Black holes are regions in spacetime where gravity is so intense that nothing, including light, can escape. Black holes form from the gravitational collapse of massive stars. The extreme gravity prevents any form of matter or radiation from escaping a black hole's event horizon. The mass of a black hole dictates the size of its event horizon. The event horizon is the boundary beyond which escape from the black hole is impossible. The spin of a black hole influences its properties and interactions with surrounding matter. Many black holes exist in binary systems, orbiting around a common center of mass. Binary black holes gradually spiral closer together over time. The emission of gravitational waves causes binary black holes to lose energy and angular momentum. As two black holes approach each other, their orbital speed increases dramatically. The space around the black holes becomes increasingly distorted due to their immense gravity. Eventually, the black holes begin to merge, forming a single, larger black hole. The collision of two black holes is an extremely violent event. This collision releases tremendous energy in the form of gravitational waves. The merger event creates a significant disturbance in the surrounding spacetime. The merger of two black holes results in a single, larger black hole. The newly formed black hole initially oscillates before stabilizing. The final state is a stable, larger black hole. Gravitational waves are disturbances in the curvature of spacetime. These waves propagate outward from the source at the speed of light. Gravitational waves are generated by violent cosmic events, such as the collision of black holes. Gravitational wave amplitude provides information about the masses of colliding black holes. Gravitational wave frequency reveals the spins and orbital parameters of colliding black holes. Analyzing both amplitude and frequency allows for comprehensive characterization of black hole collisions. The Laser Interferometer Gravitational Wave Observatory, LIGO, detects gravitational waves. LIGO uses laser beams to measure tiny changes in distance caused by passing gravitational waves. The interferometer is sensitive to changes in distance smaller than the width of a proton. Gravitational waves cause minute distortions in spacetime as they pass through an object. LIGO detects gravitational waves by measuring the changes in the length of its two perpendicular arms. The stretching and compressing of LIGO's arms creates a detectable signal that confirms the passage of a gravitational wave. The signal from LIGO undergoes processing to remove noise. Signal processing extracts the characteristics of the gravitational wave. Filtering and extraction enable detailed analysis of gravitational wave events. Gravitational wave signals are detected and represented as waveforms. Waveforms illustrate the change in strain over time caused by gravitational waves. The waveform's shape and characteristics provide information about the source of the gravitational waves. Gravitational wave signals contain information about the masses of colliding black holes. Analyzing the frequency and amplitude of gravitational waves allows for the determination of black hole masses. Mass calculation from gravitational waves relies on complex mathematical models and computational analysis. The amplitude of a gravitational wave signal is directly related to the distance of the black hole merger. Analyzing the amplitude of gravitational waves allows for an estimation of the distance to the source. Distance estimation is derived from the gravitational wave signal's amplitude. Gravitational wave signals carry information about the properties of black holes. The shape of a gravitational wave signal reveals the spin of the black holes that created it. Analyzing gravitational wave signals allows scientists to measure the spin of black holes. The signal detected confirms the existence of an intermediate mass black hole. Intermediate mass black holes were previously theorized, but lacked direct observational evidence. This detection provides the first direct observation of an intermediate mass black hole. One theory proposes that intermediate mass black holes originate from the collapse of massive stars. This stellar collapse typically occurs within dense stellar environments. The resulting object is an intermediate mass black hole. Intermediate mass black holes may form through hierarchical mergers. This process involves repeated mergers of smaller black holes over time. Hierarchical mergers contribute to the growth and evolution of black holes. Intermediate mass black holes may be primordial, forming in the early universe shortly after the Big Bang. Primordial black hole formation suggests an alternative pathway distinct from stellar collapse. The early universe provided conditions for direct black hole formation without requiring stellar remnants. Black holes significantly influence the evolution of galaxies. Black holes affect the formation of stars within galaxies. The distribution of gas within a galaxy is influenced by the presence of a central black hole. Supermassive black holes reside at the centers of galaxies. These black holes can power active galactic nuclei, AGN, emitting vast amounts of energy. Active galactic nuclei release energy across the electromagnetic spectrum. Intermediate mass black holes may have served as seeds for the growth of supermassive black holes in the early universe. These intermediate mass black holes provided a gravitational foundation for the accretion of matter, leading to the formation of supermassive black holes. The seeding process explains the rapid formation of supermassive black holes in the early universe, a phenomenon that challenges traditional black hole formation models. Gravitational wave astronomy offers a novel approach to exploring the universe. This method complements traditional electromagnetic observations, providing a more complete understanding of cosmic phenomena. By detecting gravitational waves, scientists can observe events and objects that are invisible to electromagnetic telescopes. Future gravitational wave observatories will expand the range of detectable gravitational waves. LISA, the Laser Interferometer Space Antenna, is designed to detect lower-frequency gravitational waves. Lower-frequency gravitational waves provide insights into cosmic events, Multi-messenger astronomy combines gravitational wave and electromagnetic observations. Combining different signals provides a more complete understanding of cosmic events. Gravitational waves and electromagnetic waves offer complementary information about astrophysical phenomena. Space-time is visualized as a flexible fabric that can be distorted by massive objects. As two black holes approach each other, the space-time fabric between them becomes heavily distorted. The collision of black holes causes significant ripples and waves in the space-time fabric. The merger releases immense energy. Energy propagates outward in ripples. The simulation visualizes the energy release. Data visualization graphically represents detected gravitational wave signals. Waveform analysis reveals unique characteristics of gravitational waves. Graphical representation aids in the interpretation of gravitational wave signals. Data visualization involves plotting the masses and spins of colliding black holes. This plotting helps in understanding the mass-spin relationship of black holes. Analyzing mass and spin provides insights into black hole dynamics and formation. Distance estimation accuracy is visualized to illustrate the precision of collision prediction. Graphical representations provide a clear understanding of the accuracy in estimating the distance to a potential collision. Data visualization tools enhance the understanding and interpretation of distance estimation accuracy. Stellar populations in dense clusters are simulated to understand their evolution. Simulations explore the likelihood of black hole mergers within these stellar populations. The dynamic interactions within dense clusters significantly influence the formation and merger of black holes. Hierarchical merger rates model the frequency at which smaller black holes combine to form larger ones. The model predicts the distribution of black hole masses resulting from successive mergers. Understanding merger rates is crucial for predicting the evolution of black hole populations in the universe. Theoretical models are used to estimate the density of primordial black holes. These models also predict the distribution patterns of primordial black holes throughout the universe. Understanding the density and distribution of primordial black holes requires complex calculations and simulations. Black holes exert a significant influence on the formation and evolution of galaxies. This feedback mechanism regulates star formation within galaxies by heating and dispersing gas. Simulations demonstrate how black hole feedback shapes the overall structure and properties of galaxies. Active galactic nuclei are powered by supermassive black holes at the centers of galaxies. The accretion disk feeds material into the black hole, releasing enormous amounts of energy. Jets of particles are ejected from the poles of the black hole at near light speed. Seed black holes are theorized to grow into supermassive black holes in the early universe. Modeling the growth of seed black holes helps understand the formation of supermassive black holes. The growth of seed black holes is influenced by factors such as gas density, accretion rate, and merger events. Gravitational waves span a wide spectrum of frequencies, each linked to different astrophysical events. Low-frequency gravitational waves are associated with supermassive black hole mergers and extreme mass ratio inspirals. High-frequency gravitational waves originate from compact binary systems, such as neutron star and black hole mergers. Multi-messenger astronomy correlates gravitational wave events with electromagnetic signals. Data visualization graphically represents the temporal and spatial correlation between these events. This correlation provides insights into astrophysical phenomena and validates theoretical models. LIGO is designed to detect lower-frequency gravitational waves. LIGO's capabilities extend to detecting gravitational waves from distant and massive cosmic events. The observatory's design allows for the detection of gravitational waves imperceptible to ground-based detectors. The Einstein telescope is designed with enhanced sensitivity to detect fainter gravitational wave signals. Increased sensitivity allows the Einstein telescope to observe gravitational waves from more distant and weaker cosmic events. This enhanced sensitivity enables the detection of gravitational waves that would be undetectable by current observatories. Black hole mergers are simulated in diverse cosmic environments to study their dynamics. Globular clusters and galactic centers provide distinct conditions influencing black hole merger events. Simulation results reveal how environmental factors affect the gravitational wave signatures of black hole mergers. The distribution of black holes of varying masses throughout the universe can be graphically represented. The spin of black holes, in addition to mass, is a key parameter in understanding their population distribution. Visualizing black hole populations aids in understanding the formation and evolution of galaxies. Black hole binary systems undergo orbital decay due to the emission of gravitational waves. Modeling the evolution of these systems helps predict their merger rates and the properties of the resulting black hole. The merger of black hole binaries is a significant source of gravitational waves detectable by observatories. Gravitational wave polarization reveals information about the source's orientation and motion. Polarization patterns of gravitational waves can be categorized into plus, Yao, and cross-tens modes. Analyzing gravitational wave polarization helps determine the properties of astrophysical sources such as black hole mergers. Accretion disks around black holes are simulated to understand their complex dynamics. These simulations reveal how accretion disks generate observable signals, such as electromagnetic radiation. Simulations model the complex interplay of gravity, magnetic fields, and fluid dynamics within the accretion disk. Theoretical models describe the structure of black hole event horizons. Event horizons possess properties related to gravity, space-time, and quantum mechanics. These models provide insights into the fundamental physics of black holes and their interactions with the universe. Black hole shadows are imaged using telescopes such as the Event Horizon Telescope. The Event Horizon Telescope uses a network of telescopes to create a virtual Earth-sized telescope. Data from multiple telescopes is combined through interferometry to produce high-resolution images. Simulations explore the interaction between black holes and dark matter. These interactions may produce unique observational signatures. Studying these signatures can provide insights into the nature of dark matter. Theoretical models explore quantum gravity effects in the extreme environment near black holes. These models propose potential methods for testing quantum gravity theories through observations of black hole phenomena. Observational data from black holes may provide empirical evidence to validate or refine quantum gravity models. The evolution of black hole merger rates can be graphically represented over cosmic time. Visualizing merger rates reveals trends in black hole formation and galactic evolution. Data visualization tools allow scientists to analyze and interpret black hole merger rate evolution.